cut hallucinations by smarter chunks in Python. By the end, you will build a chunking pipeline that returns cleaner supporting context. You will see fewer wrong facts, tighter answers, and a simple way to measure coverage. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Better chunking improves answer recall and reduces hallucination. The core metric we optimize is coverage, which measures whether the retrieved chunk actually contains the ground truth or supporting facts. The trade-off is simple. Smaller chunks reduce noise, but increase index size and lookup cost. Bigger chunks keep context, but can hide the answer in unrelated text. In practice, moving from blind fixed chunks to sentence-aware chunks can cut false assertions by a clear margin on small help desk corpora. Here is the intuition. You want chunks that are coherent units of meaning. Sentence-aware packing keeps ideas intact. Overlap scoring finds the chunk that most directly matches the query terms. And answer coverage is a final check that tells the model to be cautious or to fetch a different chunk. It shines when your corpus is structured prose, like manuals or guides. It struggles when the source is highly fragmented or extremely short notes. We will build a tiny demo that shows fixed word chunks, sentence-aware chunks, a naive query ranker, a comparison view, and a coverage check before answering. Now let us start by breaking the text into simple fixed-size word chunks. This snippet splits a tiny guide into fixed-size word chunks and shows sizes. It demonstrates the baseline approach where you cut by a fixed word count and label the resulting chunks with their lengths. The purpose is to make the trade-off visible. If you increase chunk size, you get fewer chunks and more context per chunk, which can raise recall but also increase irrelevant material. If you decrease chunk size, you get more precise chunks, but more items to index and higher retrieval cost. This snippet helps you choose an initial chunk length to compare against smarter strategies. Next, we will pack whole sentences into chunks to keep ideas intact. This snippet packs whole sentences into chunks to keep ideas intact. It groups consecutive sentences until a target size is reached, which keeps semantic units together and avoids chopping mid-idea. Changing the target size affects cohesion. A lower target leads to many small sentence groups, which are precise but may lose cross-sentence context. A higher target absorbs more sentences together, which can preserve necessary explanation but risks adding irrelevant content that dilutes the answer. This approach usually improves the chance that an answer appears verbatim in a chunk compared to fixed word slicing. Now we will rank those naive chunks by how much they overlap the query. This snippet ranks naive chunks by query overlap and returns the best one. Overlap scoring counts shared tokens or important query terms inside each chunk and ranks by that score. I call this overlap scoring because it directly measures shared words between the query and chunk. If you make the score stricter by weighting rare terms higher, you favor high precision at the cost of recall. If you soften it, you get broader matches that may help paraphrased queries. The snippet returns the top chunk so you can inspect what a simple lexical ranker picks versus a sentence-aware packer. Next, we will compare the naive fixed chunks to the sentence-aware chunks on the same query. This snippet compares naive and sentence-aware chunking on the query. It runs both chunking strategies and shows their top-ranked chunks side by side, so you can see which one contains better supporting facts. The comparison highlights where a fixed chunk includes unrelated paragraphs, while the sentence-aware chunk often isolates the relevant explanation. If you tune the sentence packing target, you can shift the winner. This direct comparison makes the practical trade-off obvious and gives quick visual evidence for changing chunk sizes before you move to embeddings or semantic retrieval. Finally, we will check that the chosen top chunk actually covers the answer to avoid feeding the model misleading context. This snippet checks answer coverage in the top chunk to reduce hallucinations. It scans the top-ranked chunk for key answer tokens or phrases, and computes a simple coverage score that estimates whether the chunk contains the facts the model needs. If coverage is low, the pipeline can either fetch the second chunk, expand the chunk window, or abstain and ask for clarification. Raising the coverage threshold makes the system more conservative and reduces hallucination, but increases fallbacks and potential latency. Lowering it returns answers faster, but risks unsupported claims. This check is the safety net for a retrieval-augmented setup. Recap 3 crisp points. Better RAG chunking keeps meaning intact, ranks chunks by query overlap, and verifies answer coverage. Use it when your corpus is narrative or instructional, and hallucinations matter more than raw speed. One caveat: it can increase index size and lookup cost when you favor smaller, safer chunks. Next step: tune the chunk size and the coverage threshold together. Then scale evaluation on a larger corpus and add an approximate nearest neighbor index if you need speed. Try a grid of chunk sizes and coverage values and measure recall and hallucination rate. If practical AI engineering helps you build reliable LLM apps, subscribe and watch the AI engineering videos.